Okay, good morning students. So in the last class we have discussed about the basics of differential amplifier. So the differential amplifier amplifies the difference between two input voltages, right? So it amplifies the difference between two input voltages. So the two inputs are V1 and V2. So that's why the output is directly proportional to the difference of two inputs. So we can say that V0 is directly proportional to V1 minus V2. That is the function of the differential amplifier. So then there are two modes in the differential amplifier. So one is differential mode and the another one is common mode. So we can operate the differential amplifier in two modes, in differential mode and in common mode, right? So and we have seen about CMRR, common mode rejection ratio. So CMRR means how effectively we can eliminate the noise, right? So that is the ability of a differential amplifier to reject common mode signal is expressed by the CMRR, common mode rejection ratio. I am getting the disturbance. Okay, so CMRR is defined as the ratio of differential gain to common mode gain, right? And these are the BJT differential amplifier circuit diagrams. So here the two emitter resistors are combined and the two collector resistors are combined. So we are using the two transistors of same characteristics, having the same characteristics. Here the two resistors are same, it has equal value, and the two collector resistors are also same, right? So to form a differential amplifier we require two transistors and two emitter resistors and two collector resistors and the two input voltages, so V1 and V2. So up to this we have discussed in the last class, right? So in the differential mode we are getting the higher gains, whereas in the common mode we are getting the lower gains. Okay, in the differential mode we are getting the higher gains, in the common mode we are getting the lower gains. Today we will see the configurations of the differential amplifiers. So how many differential amplifiers are there? There are four different types of differential amplifiers are there. See here, dual input balanced output, dual input unbalanced output, single input balanced output, and single input unbalanced output. So we will see what is balanced and what is unbalanced, right? So there are four different types of differential amplifiers. If you see the diagrams, see here we are having four diagrams here. So if you see the first diagram, here the two collector resistors are combined and the two emitter resistors are combined. Here we are having two power supplies, plus VCC and this minus VEE, right? And in the circuit we are having two inputs, that is V1 and V2. So in the first diagram the output is taken between two collectors. See here, the output is taken between two collectors, right? The output is taken between two collectors. So this type of circuit is called as dual input balanced output. Dual input balanced output. See here, if output is taken between two collectors, if the output is taken between two collectors, that differential amplifier is called as balanced output differential amplifier. If the output is taken between two collectors, that differential amplifier is called as balanced output differential amplifier. So here we are taking the output between two collectors, right? So it is the collector of Q1 and it is the collector of Q2. So the first diagram, it is the dual input. We are having two inputs, V1 and V2. So it is a dual input balanced output differential amplifier. So just compare the four types. If you see this diagram, here we are having only one input and the another input is grounded. In this diagram, we are having one input and second input is grounded, right? And the output is taken between two collectors. Here also the output is taken between two collectors. So this type of differential amplifier is called as single input balanced output differential amplifier. Single input balanced output differential amplifier, right? So first one is dual input balanced output, second one is single input balanced output. So this diagram is single input balanced output differential amplifier. If you see this one, here we are having two inputs V1 and V2, but the output is taken at only one collector with respect to ground, right? So in this diagram, the output is taken at one collector with respect to ground. So this type of differential amplifier is called as dual input unbalanced output differential amplifier. Dual input unbalanced output differential amplifier. So in the last diagram, we are having only one input, that is V1, and the second input is grounded. Here this input is grounded. Here the output is taken at one collector, right, with respect to ground. So this type of differential amplifier is called as single input unbalanced output differential amplifier. Single input unbalanced output differential amplifier, right? The construction is same for all differential amplifiers, but if the input is 1, so we are having only one input, that is called single input differential amplifier. If the output is taken between two collectors, that differential amplifier is called as balanced differential amplifier. If the output is taken between one collector with respect to ground, that is called unbalanced. So this diagram is balanced output. Here this one is unbalanced output. Clear? So these are the four different types of differential amplifier configurations. So every differential amplifier having two power supplies, plus VCC and minus VE, right? And two emitters are combined and two collector resistors are combined. So everything is same, but the difference is, if you take the output between two collectors, that is called balanced output differential amplifier. If you take the output between one collector with respect to ground, that is called unbalanced output differential amplifier. If you are having only one input, that is called single input differential amplifier. If you are having two inputs, that is called dual input differential amplifiers, right? So next we will see the DC analysis and AC analysis of the differential amplifiers. If you see the DC analysis, see here, the DC, while calculating the DC analysis, the AC input signal will be 0. One second. Okay. In the DC analysis, we need to calculate. In the DC analysis, we need to calculate ICQ and VCQ. That is the operating point coordinates. ICQ and VCQ are the operating point coordinates. We have to calculate ICQ and VCEQ, right? So Q means quiescent values. So in the DC analysis, we are going to calculate the operating point coordinates, that is ICQ and VCEQ, that is equal to IC and VCE. Finally, we are calculating the IC and VCE values, right? So applying KVL to base emitter loop. So see here, it is a base emitter loop. So if you apply KVL to this base emitter loop, then the equation will be like this. So the voltage drop across RS1, this voltage drop is, that is minus IB RS, right? So this resistor is RS. We are having the two transistors, right? Two resistors, that is RS1 and RS2. Simply we can take RS. So the base current is flowing through RS. Here it is a base terminal, right? The base current is flowing through RS. So the voltage drop across this resistor is this one, IB into RS, right? And the voltage between base and emitter, so this voltage is VBE, right? This voltage is VBE. And this voltage drop, so what is the voltage drop across RE? Here we are taking 2IE. So the voltage drop across RE is IE into RE, but we are taking 2IE. Why? Because one emitter current is coming from this Q1 transistor and another emitter current is coming from Q2 transistor. So two emitter currents are flowing through emitter resistor. So two emitter currents are flowing through the emitter resistor. So that's why here we have taken 2IE. So this voltage drop, the voltage drop across RE is 2IE RE. So plus VE equal to 0. So if you apply the KVL to this base emitter loop, then we will get, so this equation according to polarities, based on the polarities, we can write minus IB into RS minus VBE minus 2IE RE plus VE equal to 0, right? So this voltage drop is IBRS, this voltage is VBE, that is the voltage between base and emitter, that is a constant voltage, and this voltage is 2IE into RE. So two emitter currents are flowing through RE, that's why we have taken 2IE. So plus VE equal to 0. But we know that IC equal to beta IB, right? The relation between collector current and base current. So IC equal to beta IB and IC equal to IE. So collector current approximately equal to emitter current and IC equal to beta IB. Here beta is the forward current gain in CE configuration. So this CE configuration, right? So beta is the forward current gain in CE configuration. So based on these relations, we can write IB equal to IC by beta. Okay, we can write IB equal to, from this relation we can write IB equal to IC by beta and IC equal to IE. So we can write IB equal to IE by beta. Clear? IB equal to IE by beta. So substitute this IB equation in this first KVL equation. So then we will get minus IE into RS by beta. So minus VBE minus 2IE RE plus VE equal to 0. Right? So just we are substituting this IB equation in the equation 1. So then take IE is common, then we will get minus RS by beta minus 2RE plus VEE minus VBE equal to 0. So from this we can write IE equal to, so VEE minus VBE by this one, RS by beta minus 2RE, RS by beta minus 2RE. One second. Okay. So in practical RS by beta is low. So actually beta ranging from 50 to 500. So that's why this value is low. So finally we can take IE equal to VEE minus VBE by 2RE. So IE equal to VEE minus VBE by 2 RE, right? Here minus minus we cancel, so IE equal to VEE minus VBE by 2 RE. That is the collector current equation. That is approximately equal to emitter current equation, right? So remember this equation is, emitter current equation is IE equal to VEE minus VBE by 2 RE. So here we are applying the KVL to the base emitter loop and finding the emitter current. So next we need to find out the collector emitter voltage VCEQ, right? So the coordinates of operating point are IC and VCE. So that's why we need to calculate VCE also. Here the collector voltage of Q1. See here, the collector voltage of Q1. The collector voltage of Q1, right? So it is VCC minus this voltage drop. This voltage drop is IC into RC. This voltage drop is IC into RC. This is the VCC. So the voltage drop at collector of Q1 equal to this voltage minus this voltage. So we can write VCC minus IC into RC. See here, the collector voltage of Q1, that is the collector voltage, VC equal to VCC minus ICRC. But we required VCE. So VCE means the voltage between collector and emitter. So this voltage, VCE means the voltage between collector and emitter, right? So VCE equal to this voltage, VC minus VE, collector voltage minus emitter voltage. So VCE equal to VC minus VE. So we can write VCE equal to VC minus VE. So finally VC equal to VC minus VE. In place of VC we can write VCC minus IC into RC. So and VE equal to minus VBE. Okay. So VCE equal to VCC plus VBE minus ICRC. If you substitute this VC and VE in this equation, then you will get VCE equal to VCC plus VBE minus ICRC. So these are the operating point values. So it is the DC analysis. In the DC analysis, we are calculating the operating point values, right? So operating point values means IC and VCE. That is equal to IE and VCE. IE equal to ICQ, right? That is equal to IC. So all these are related. So in the DC analysis, we are calculating the operating point values. That is IC and VCE values, right? IC and VCE values. So that is about DC analysis. Next, if you see the AC analysis, see here, this is the AC analysis. So here we are having two loops. It is the first loop and it is the second loop. So apply KVL for these two loops, then we will get the first equation will be, so this equation V1 equal to IB1 is flowing in this direction. So here IB1, IB2 are the small letters, right? So we are calculating the AC analysis. That's why this is IB1, RE dash. These are all the denoted with small letters. So V1 equal to RS1, this voltage drop. RS1 into IB1. The IB1 is flowing through RS1. So that's why we can write V1 equal to RS1 into IB1 plus this voltage drop. This voltage drop is IE1 into RE dash. IE1 into RE dash, right? So IE1 is flowing through RE dash plus the voltage across RE. So this IE1 is flowing through RE and IE2 is flowing through RE, right? So we can write IE1 plus IE2 into RE. The voltage drop across RE is IE1 plus IE2 into RE. So in the DC analysis, we are taking capital letters. right? So 2 IE. Here we are taking capital IE. But in the AC analysis, we are taking small IE, right? So that is the difference. If you apply KVL to the second loop, so V2 equal to this RS2 into IB2. So this voltage drop is RS2 into IB2, and this voltage drop, that is IE2 into RE dash, and this voltage, that is IE1 plus IE2 into RE. So apply KVL to these two loops, then we will get these two equations, V1 and V2. So here substitute the current equations. So current equations means we know that IB1 equal to IE1 by beta, right? See here, IB1 equal to, here IB equal to IE by beta, so IB1 equal to IE1 by beta. So these are the current equations. So substitute these current equations. So then IB1 equal to IE1 by beta, and IB2 equal to IE2 by beta, right? So if you substitute these equations in V1 and V2, then we will get V1 equal to RS1 by beta into IE1 plus RE dash into IE1 plus RE into IE1 plus IE2. In a similar way, V2 equal to RS2 by beta IE2 plus RE dash IE2 plus RE into IE1 plus IE2. So in the AC analysis, we are applying the KVL to the two loops, is the first loop and second loop. Then we are substituting the current equations IB1 and IB2. If you rearrange these equations, see here, RS1 by beta and RS2 by beta are very small. So here RS1 by beta, right? Here we are having RS1 by beta and RS2 by beta. So beta value is high. That's why RS1 by beta and RS2 by beta, we can neglect these two values. So again, assuming this RS1 by beta and RS2 by beta are very small in comparison with RE and RE dash. So when you compare with RE and RE dash, this value is small. So therefore we can neglect these two terms. So after solving these two equations, then we will get V1, V2 like this. So RE dash plus RE into IE1 plus RE into IE2, and V2 equal to RE into IE1 plus RE dash plus RE into IE2. So from these two equations, calculate IE1 and IE2. From these two equations, calculate IE1 and IE2. So then we will get these two, IE1 equal to RE plus RE into V1 minus RE V2 by RE dash plus RE whole square minus RE square. These are the IE1 and IE2 equations, right? So here in the AC analysis, we need to calculate the differential gain. In the AC analysis, we need to calculate the differential gain. In the DC analysis, we need to calculate the operating point values, but in the AC analysis, we need to calculate the differential gain. So here the output voltage V0 equal to Vc2 minus Vc1. So Vc2 is the collector voltage of Q2 and Vc1 is the collector voltage of Q1. So we can write V0 equal to Vc2 minus Vc1. V0 equal to Vc2 minus Vc1. So substitute. So Vc2 is Rc into Ic2 and Vc1 is Rc into Ic1. So take common Rc. Then we will get Rc into Ic1 minus Ic2. In the similar way, we can write IE1 in place of Ic1 Ic2. We can write IE1 IE2. So substituting IE1 and IE2 in the above equation. So here we are having IE1 IE2 equations, right? So substitute these IE1 and IE2 equations in this equation Rc into IE1 minus IE2. So substitute. So V0 equal to Rc into, so this is the IE1 equation and it is the IE2 equation. Then we will get V0 equal to, so these two terms will cancel, RC by RE dash into V1 minus V2. RC by RE dash into V1 minus V2. So here V1 minus V2 is nothing but VD, differential voltage, right? So V1 minus V2 is equal to, V1 minus V2 equal to VD. So then we can write differential gain equal to V0 by VD, output voltage by input voltage. This is not VC, it is V0. V0 by VD. So AD equal to, that is the differential gain equal to V0 by this VD. That is V1 minus V2 is nothing but VD. So it becomes RC by RE dash. So it is the AC analysis. So in the AC analysis, we are calculating this differential gain. So here the differential gain is depends on collector resistor and this RE dash, right? So the differential gain depends on RC and RE dash. If you see the formulas, so what is in the DC analysis, what is the IE equation? So IE equal to this one, IC or IE equal to this VE minus VBE by 2RE, this one VE minus VBE by 2RE. So that is one important formula. And second one is VCEQ, that is VCEQ equal to, or VCE equal to this one. It is a second important one formula. VCC plus VBE minus ICRC. So these two are the DC analysis formulas. If you see the AC analysis, here the differential gain is RC by RE dash, right? So these three formulas are important. Next we will calculate input resistance. So how to calculate the input resistance? RI1 for the first stage, right? So it is the ratio of input voltage to input current. The input voltage is V1 and the input current is IB1. Then the output is shorted, right? So it is defined as the ratio of input voltage to input current. Then V2 equal to 0. So substitute here IB1. IB1 equal to IE1 by beta. So IB1 equal to IE1 by beta. When V2 equal to 0, then you will get the input resistance RI1 equal to this one. The input resistance RI1 equal to beta RE dash into RE dash plus 2RE by RE dash plus RE. So if you see these relations, RE dash plus 2RE is greater than 2RE and RE dash plus RE, similarly RE dash plus RE is greater than RE, right? So finally we can write input resistance for the first stage, it is 2 beta RE dash. 2 beta RE dash. So these two terms will cancel. Then we will get 2 beta RE dash. So here for the second stage the input resistance is RI2 equal to 2 beta RE dash. So same RI1 equal to RI2. The factor of two arrays, why these two comes into picture? The factor of two arrays because of the RE dash of each transistor is in series, right? See here in the AC analysis. So this RE dash, these two are in series. So that's why in the input resistance it becomes, the input resistance becomes this one, Ri equal to 2 beta Re dash. So Ri1 equal to 2 beta Re dash and Ri2 equal to 2 beta Re dash. So this is about the differential configurations, the differential amplifier configurations and the DC analysis of the differential amplifier and the AC analysis of the differential amplifier. So one more thing, it is how to calculate the output resistance. The output resistance is defined as, it is the equivalent resistance measured at one output terminal with respect to ground, right? So here R01, R02 equal to RC. So the first stage and the second stage output resistance equal to collector resistance RC. Why? Because the output resistance is measured with respect to one of the output terminal with ground, with respect to ground. So if you see the Example here, the following specifications are given for the dual input balanced output differential amplifier. The given values are RC equal 2.2 kilo ohms, RV 4.7 kilo ohms, RIN1 equal to RIN2, so that is equal to 50 ohms, plus VCC equal to 10 volts, and minus VGE equal to minus 10 volts, and beta equal to 100, VB equal to 0.7 volts, right? For germanium it is 0.7, sorry, for germanium it is 0.3, for silicon it is 0.7 volts. So here determine the voltage gain, determine the input resistance, determine the output resistance. So based on this we can calculate the, based on the formulas what we have discussed now, we can calculate the voltage gain, input resistance and output resistance. Okay, see here the comparison table is important. So for dual input balanced output differential amplifier, the differential gain is RC by RE, right? So for balanced output means the output is taken between two collectors. For unbalanced output it becomes RC by 2 RE dash. For unbalanced output it becomes RC by 2 RE dash. So the output is taken between one collector with respect to ground. So that's why the 2 will come into picture, right? So that is the differential gain. So the differential gain is same in the dual input balanced output and single input balanced output. So in these two configurations, in the balanced output configurations, the differential gain is same, right? In the unbalanced output, in this configuration the differential gain is same. So here RC by 2 RE. So here also the differential gain is RC by 2 RE. The input resistance and output resistance is common for all configurations. The input resistance and output resistance is common for all configurations. So it is 2 RE into beta, 2 RE beta, that is the input resistance for all configurations, and output resistance is RC. It is also same for 4 configurations. So it is the comparison of differential amplifiers. Okay. So any doubts? So with this we are going to stop the presentation. Any doubts? So 1 minute I will take the attendance.